Hey guys, let's continue on with our talk from chapter 7. So we're going to be starting with section 7.5 and we'll be going through 7.7 today. So make sure that you read and take notes over that. Pay attention. This is counting as your lecture for today. I'm sorry that I am not there. Just so you know what's going on. Friday during sixth period, I got a call from the nurse that my son, Christopher, my oldest, who's 9 and struggles with arthritis pretty bad in his right knee, had an accident on the playground and he ended up breaking his leg. So, been a pretty rough weekend over here. He's in a lot of pain. So I'm home with him today playing Dr. Mom and helping him. He's having a hard time moving. And trying to get him in to see an orthopedic doctor to make sure he doesn't need surgery or anything. So, if you can, send him some prayers. It's been pretty hard, but I will be back this week. My husband and I are going to take turns helping him out while he's recovering. So let's go through this. Don't forget, next Wednesday your project is due, and then next Thursday is your written test over chapter 7. So here we go. So far, when we've been dealing with Lewis structures and everything, we've been looking at making sure everybody is happy and that they're fulfilling the octet rule, remember, which is where they have 8 valence electrons around them. Well, like everything else in science, there are going to be some exceptions to this. So let's talk about those. One exception. Some molecules have an odd number of valence electrons to share, and so sometimes this makes them look kind of funky. And so here's your example. It would be nitrogen dioxide. And so if I were to draw the Lewis structure of this, it would look kind of like this. Okay. Now, nitrogen, if you look on your periodic table, starts out with 5 valence electrons. And so when I do the Lewis structure, it ends up looking like this. And what have I told y'all? We don't like lonely dots. That's no. But it happens. This is why frequently what you will see happen is this nitrogen dioxide will turn into the nitrate ion and will have a -1 charge, meaning that he's gained 1 electron. And you can, by looking at that Lewis structure, you should be able to tell where that goes. So that's a problem, in our minds, but this is an exception. This does happen. This little lonely dot electron that we don't like actually has a name, and you need to know what it's called. It's called a free radical. Now, if any of you guys are into beauty products, you've heard about free radicals and how horrible they are. Free radicals can be blamed for different diseases and aging, and they're yucky and we don't want them. And so they tell you eat blueberries and other foods that are full of antioxidants to get rid of these free radicals. Because what happens is, like I just pointed out, this guy really wants 1 electron so that he can make this nitrate ion. And so what he'll do is he'll steal an electron from a perfectly fine, healthy cell, which by stealing that electron, he has majorly hurt that cell. And so that's why they tell you, fill your body with antioxidants so that they don't steal, that those free radicals aren't left to steal electrons from happy, healthy cells. So there's one exception. The second one is that there are going to be some elements that are happy with fewer than 4 pairs of valence electrons. The big one to know would be boron. Aluminum can be another one. And so these guys are happy with only 6 electrons, 3 pairs around them. So like if you do the Lewis structure for BF3, you're going to have the boron surrounded by 3 fluorines. And if you count those up, he's got 2, 4, 6 electrons around him, and boron is perfectly happy like that. So I do want you to know for sure that boron is one that is happy with less than 8 electrons. Aluminum is another one. And then there are going to be some times that they are okay with more than 8. And so a common example would be sulfur hexafluoride, or SF6. So this was BF3 over here. This one is SF6. Again, you guys should have your notes out and be writing down these examples and what I'm writing. This is counting as lecture. I'm not going to go back over this. And so sulfur is one example here where he's fine. I'm not going to go through it all, but here's an F. Basically, he would end up with a Lewis structure that has sulfur in the middle, surrounded by 6 fluorine atoms, and of course they all need their lone pairs around them, so we'll do all the dots, blah, blah, blah. Okay, so there's your octet exceptions. Some guys have an odd number, so you get a free radical, you get a lonely electron. Some elements are happy with less than 8 valence electrons. Boron is a good example there. And then in some guys, they're happy with 8. Some atoms are happy with more than 8 valence electrons. They get super greedy. And so sulfur was an example there. All right, moving on. Molecular orbital theory. Sometimes you will see this called the MO theory. So if you see MO theory, it's molecular orbital. Reason why we had to come up with this, like science, theories are models. When we come up with new information, we have to adjust our current standing theories. And so the valence bond theory was working, but when they started to look at diatomic oxygen, they noticed that there was some irregularities and things about oxygen that the valence bond theory could not explain. And so because of that, they had to kind of adjust. And so they came up with what's called the molecular orbital theory. And it says that when a molecule comes together, and so let's just do generic. We've got molecule A bonding to 2 atoms of molecule B, okay? You have 3 atoms coming together to form one molecule. Well, atom B, atom A, and atom B all come to this union with their own orbital surrounding them. But when they come together and bond, what they'll do is they'll trade in these individual orbitals, and they'll come together and they'll form new orbitals around the molecule called molecular orbitals. So they give up their atomic orbitals to come together and bond and unite to form completely new molecular orbitals that will surround the entire molecule. And so a stupid example I often give with this is it's like you're getting married to someone. You have a set of dishes. You've got enough settings for 10 people. The person you're marrying has their own complete set of dishes for 10 people. They're different. They're unique to you and him as an individual. But when you come together and marriage, you need to give up those individual dish settings to have ones for you as a couple. And you need to combine in such a way that it's equal to the amount you both had. So I have 10 place settings, they have 10 place settings. So we're going to give those up. We're going to go register for 20 place settings of a completely new dish settings for us as a couple. So kind of a dumb way of looking at it, but if it helps, great. Basically, when these guys come to bond, when that bonding happens, they give up their individual atomic orbitals. They give up their right to that. They bond together, and they will form these completely new molecular orbitals. And it needs to be the same number. So if, again, I'm trying to bring this down as much as possible so it's easy. Let's say atoms B, A, and B each have 2 orbitals surrounding them. So then that means, because they each have 2 orbitals, we should end up with 6 new molecular orbitals around this molecule. And like everything else we've talked about in chemistry this year, they will be ranked in order of increasing energy. And if you remember, electrons like to be as low energy as possible, like teenagers. And so that means that the lowest energy orbitals will get filled first and then work their way up. Within this molecular orbital theory, you do end up with two different types of orbitals. You end up with bonding and anti-bonding orbitals. They are exactly what they sound like. A bonding orbital is where a bond will form. A bonding orbital is a orbital that is in the correct place for a bond to form. These bonding and anti-bonding orbitals are a way to predict if a bond will or will not form between two atoms. A bonding orbital is going to be an orbital in which the electrons reinforce each other. In a bonding orbital, the electrons are going to be located between the nuclei. So that means here's the nucleus of one guy, here's the nucleus of the other. The electrons are going to be shared in an orbital right in between these guys. Well, what do opposite charges do? They attract. So if I have an area of negative charge in between these two positive nuclei, there is going to be bonding there. And that should make sense. This opposite charge, that electrostatic force, is going to keep those atoms together. So there will be bonding. These bonding orbitals tend to be lower in energy, so electrons are going to head there first. Now, these anti-bonding orbitals, just like it sounds, it will not allow a bond to form. So there will be no bond forming in an anti-bonding orbital. And so these orbitals, the electrons come together in such a way that they kind of interfere, they kind of are disruptive to each other. An anti-bonding orbital is actually going to occur outside of the nuclei. So here's two anti-bonding orbitals. If I have a bonding orbital right here, sure, this nuclei might be attracted, but in order for a bond to occur, I would need something on the other side, and there's not. So there's no bond going to be formed. There's no two atoms coming together because these anti-bonding orbitals are, one, very high in energy, and two, they are located outside of the nuclei. That is not going to allow a bond to form. So a bonding orbital needs to be in between the nuclei. That way the electrostatic force is going to keep those atoms together. All right, let's go into a little bit of geometry here. Make sure that you've taken notes over 7.5, 7.6, and let's start 7.7. Go back and watch this again if you need to. In order to help yourself, you may want to have a book open to page 179. There's a very helpful chart there. If you do not remember Lewis structures, I'm not going to go back and reteach it. It is up to you to take the initiative, go look up YouTube videos, go back to your old notes, read the book, come to helps, do whatever you need to, find a friend to help you with it. I've told you guys this. I said it so I was blue in the face last chapter. That if you do not get Lewis structures, you will not be successful in chapter 7. Here is why. You need to know how to do Lewis structures in order to work with Vesper. So I'm going into this assuming you know Lewis structures, and if you struggled with it, you need to be practicing because I'm not giving you Lewis structures. I will be giving you formulas. You will be drawing Lewis structures to determine shape. All right, here we go. Vesper, say it Vesper, Vesiper, I don't care. Valence shell electron pair repulsion theory. You need to know those words. Acronym's great, but you need to know what it stands for. Valence shell electron pair repulsion theory. Electrons have a negative charge. What do like charges do? They repel, hence the repulsion. We're talking about electrons, and specifically electrons pairs. That could be a bond or it could be a lone pair, repelling each other. This is going to determine the shape of your molecule. Because electrons are going to repel each other as far away as possible, as geometrically possible, there are going to be very specific shapes based on this. Now, here is what I say to help. You will draw your Lewis structure. That is your first step. Draw the Lewis structure. Second, count up how many sides around the central atom. Write that down. Count up electrons around the sides of the central atom. How many sides does, oops, nope. How many, well, that is not what I wanted. How many sides does a central atom have? Well, 4. So here is my, oops, I want my pen back. Here's my atom. You can have electrons on each side. That's 4 different sides. That is 4 areas where you can have electrons. So this is what I mean by counting up electrons around the central atom. You can have 1 area of electron. You can have 2. You can have 3, or you can have 4. Here's how it's going to look. Write this down. This area of electron, it could be a lone pair. So it could be the dots. It could be a single bond. It could be a double bond. It could be a triple bond. I don't care if it's dots, 1 dash, 2 dash, 3 dashes. If there are electrons on that side, it counts. The lone pair counts as much as a single bond, counts as much as a double bond, counts as much as a triple bond. As long as there are electrons on that side, you count it. And then the third thing you need to look at is to see those areas where there are electrons, are they bonded or are they lone pairs? That matters. So draw your Lewis structure, count up how many sides around that central atom have electrons, whether it's lone pair, single bond, double bond, or triple bond, and then look to see out of those areas of electrons, are they bonded or are they lone pairs? So here's a couple of examples to get you started. So the first one they give you is carbon tetrachloride. So you got CCl4. And so you're going to have carbon. And carbon has 4 valence electrons. This tells me that I have 4 chlorines. Where can I put those 4 chlorines? Well, on one on each side of my carbon. Don't forget, these lone pairs around the chlorine are important. I take off if you don't have those. Because remember, chlorine has 7 valence electrons, which is why it fits perfectly around this carbon. All right, so I draw my Lewis structure, okay? Second thing I need to do is I need to count up how many sides of that central atom have electrons around them. Remember, electrons can look like dots or dashes. That's really what you're looking for. So I look at my central atom. I look at that carbon. How many sides have electrons around it? Well, I have electrons here. I have electrons here. I have electrons here. I have electrons here. That is 1, 2, 3, 4 sides surrounded by that have electrons. So because I have 4 areas of electron, the next thing I need to look at is how many of those are bonded or lone pair. Well, if I look at this, they're all bonds. So if I have 4 areas of electron and all 4 are bonded, this is probably one of the easier ones to recognize. This is called tetrahedral. And if you remember, that prefix tetra is 4. So it kind of almost starts to look like a cross. That's an easy one to see. Okay. The next one they give you is trigonal planar. So let's talk about that. So here is what trigonal planar is going to look like. So let's see, let's go back. CH2O. Okay, so first thing we got to do is we got to draw our Lewis structure. I'm not going through the whole process of drawing the Lewis structure. If you need to, then go for it. Here's my Lewis structure. Okay, so I drew the Lewis structure. Now I need to count up how many areas of electrons around that central atom. This carbon is my central atom. I have 1 area there. I have 2 areas, and I have 3. So I have 3 areas of electron. My next thing I need to look at is those areas of electron. Are they lone pair or are they bonded? Basically, are they dots or are they dashes? Well, single bond, double bonds. They're all bonded. So if I end up with 3 areas of electrons around my central atom and all 3 are bonded, this is trigonal planar. And again, this was shown in the ed puzzle y'all did last week if you need to go back and look at it for help. So there's your example of trigonal planar. 3 and 3. 3 areas of electron, 3 bonded. When you had 4 and 4, when you had 4 areas of electron and 4 were bonded, you had tetrahedral. Okay, and think about this. Tri is 3. Okay, the last one I'm going to show you for today is linear, and that one is super easy. So let's do that one real quick. On the paper you're going to be working on today, you might see other shapes. You might see pyramidal is probably the only other one. Pyramidal and bent. I'll be going over those tomorrow, but you might see those on the paper, and that's okay. Use that chart on 179 to your advantage. Draw the Lewis structure. Count up how many areas of electron around that central atom, and then see if those areas of electrons are bonded or lone pairs. So we have carbon dioxide as our example for linear. So here's the Lewis structure. Okay, here we go. Looking at that central atom, count up the areas of electron density. I have a double bond on this side and a double bond on that side. So that means I have 2 sides of that central atom that have electrons. I don't care that they're double bonds. I have 1 area of electron density here. I have 1 here. So I have a total of 2 areas of electron density, meaning that I have 2 sides that are completely empty. And because both of those areas of electron density are bonded, I have 2 areas of electron density. Both are bonded. This is linear. And that's going to be a completely 180-degree angle. Remember, these electrons are going to get as far away from each other as possible. Okay, so make sure you've taken notes over this. We'll be coming back later talking about hybridization and going into pyramidal and bent, but use 179 to help you on that worksheet that you will be doing, and I hope to see you guys soon.